This video on matrix inverses has three objectives. First, we're going to use non-singular matrices to solve multiple systems at the same time, all at once. Then we're going to determine if a given matrix is invertible, and if it is invertible, find its inverse. And then finally, we're going to see how unitary matrices behave inside inner products. We'll define an n by n matrix A to be invertible if there's another n by n matrix C such that C times A is the n by n identity, and A times C is also equal to the n by n identity. We call C the inverse of A, and we write C equals A with a superscript minus 1, so this is read as A inverse. An important theorem here tells us that the inverse of a matrix is unique. That allows us to refer to the inverse, since there's only one. We have an example here that I'm not going to go through all the details of. Make sure you read this in the lecture notes. But it essentially talks about solving n matrix equations all at once. So if I have ax equals b1, b2 down to bn, A is the same coefficient matrix, but the constant vectors are different in every case. The punchline here is that you can just augment A with each of the constant vectors, row reduce it. If A is a non-singular matrix, it will row reduce to the identity, and then each of these columns will row reduce to some other vectors called C's here, and the C's are the solutions to the corresponding systems. In other words, AC1 is B1, AC2 is B2, down to ACN is Bn. This example also gives us this nice result here that A times C equals B, if I define C to be the matrix whose columns are the vectors C1, C2 to Cn, and B is the matrix whose columns are B1 to Bn. This we'll use to prove a theorem later. This example relies on the fact that the matrix A is a non-singular matrix. Okay, let's see how it works with a specific example. Let's say I've got this 3 by 3 matrix A, and I've got three different vectors in C3. Now I want to solve these three matrix equations, which correspond to three systems, Ax equals B1, B2, B3, and I'd like to do it all at once. Well, I can do that if the matrix A is non-singular. So if we row reduce A and it row reduces to the 3 by 3 identity, I know it's non-singular. We could do that separately, but we might as well do everything all at once. In other words, let's take A, augment it with B1, B2, and B3, and get one big matrix and row reduce the whole thing. If the first partition, the first three columns, is the identity matrix, well then we know that A row reduces to the identity and it is non-singular, and the columns that are to the right of A will be the solutions to this system. And if A does not row reduce to the identity, then this technique won't work. Okay, so here's A augmented with B1, B2, B3. We row reduce it on a computer, and sure enough, the first three columns are the three columns of the 3 by 3 identity. So these three columns are the solutions to our corresponding matrix equations. So the solution to Ax equals B1 is the set containing 1, 1, 0, the first of the columns here. Solution to Ax equals B2 contains 1, 0, 1, the set containing that column vector. Solution to Ax equals B3 is the set containing 1, 2, 1. We can use the result from the first example to compute the inverse of a matrix. We'll see in a little bit that non-singular and invertible are really the same thing, that a matrix is non-singular if and only if it's invertible. This theorem tells us that if I take a matrix A, an n by n non-singular matrix A, augment it with the n by n identity, if it row reduces to the n by n identity and C, then AC is equal to In and C is equal to A inverse. And the proof is essentially just referencing the first example that we did. So we can use that theorem to do problems like this. We're given a matrix, and we're asked if it's invertible, and if it is, find the inverse. Well, we take the matrix, we augment it with the same size identity. So this is a 3 by 3 matrix. We augment it with the 3 by 3 identity and row reduce it. If we don't get the 3 by 3 identity here, we're done. The answer to the first question is no, it's not invertible. And of course, if it's not invertible, we're not going to find its inverse. If we do get the n by n identity, or the 3 by 3 identity in this case, which we got, then the answer to this question is yes, it is invertible. And moreover, here's A inverse right here. These three columns are the three columns of A inverse. So we just copy and paste these into a new matrix, and there's A inverse. Here are some properties of invertible matrices. The inverse of the inverse gets you back to the original matrix. If I have two matrices that are invertible, then their product is also invertible, and the inverse of the product is a product of the inverses, but in reverse order. So the inverse of AB is B inverse times A inverse. If a matrix is invertible, so is its transpose, and the inverse of the transpose is equal to the transpose of the inverse. In other words, the order doesn't matter. And finally, if a matrix is invertible and alpha is a non-zero scalar, then alpha times A is also invertible, and the inverse of alpha A is 1 over alpha times A inverse. These two theorems lead up to the main theorem here, the equivalence of non-singular and invertible, which I already mentioned. If A is an n by n matrix, then it's non-singular if and only if it's invertible. The if and only if means that this is equivalent. Non-singular and invertible are logically equivalent. You could think of them as just different names for the same thing. The first theorem up here says that if A and B are n by n, then A times B is non-singular if and only if both A and B are non-singular. And then this one says if A and B are n by n and A times B is the identity, then B times A is also the identity. That brings us to one of the main theorems in the course, the invertible matrix theorem. This is a large equivalence theorem. These statements are all logically equivalent. So if A is an invertible matrix, then all these things are true. Of course, as we just saw, A is non-singular, A is row equivalent to the n by n identity matrix, A has n pivot positions, Ax equals 0 has only the trivial solution, etc., etc. And as you can see, there are quite a few logically equivalent statements here. We will refer to the invertible matrix theorem, which is abbreviated IMT for short, often throughout the course. It's a very powerful theorem because if we can figure out if any one of these things is true, then we know that they're all true. Likewise, if any one of these is false, we know that they're all false. Now we come to our third objective about unitary matrices. We're going to define a unitary matrix. We'll say U is a unitary matrix if it's n by n and it satisfies this equation, U star U equals I. Remember, U star is the adjoint, so the adjoint of U times U is equal to the identity. Any matrix that satisfies that property is called a unitary matrix. If U is unitary, then it's invertible, and its inverse is its adjoint. This theorem tells us that the columns of an n by n matrix U form an orthonormal set if and only if U is a unitary matrix. Among other things, this is really useful if we are given a set of column vectors and we want to decide if they're an orthonormal set. Simply form a matrix, U, whose columns are these vectors in the set, and compute U star U. And if you get the identity matrix, then U is unitary, and if you don't, U is not unitary. Finally, we see how unitary matrices behave inside inner products. If U is a unitary matrix, and X and Y are in Cn, then the inner product of Ux with Uy is equal to the inner product of X with Y, and the norm of Ux is just equal to the norm of X. This property is a little different than the one we saw about Hermitian matrices. In that case, Hermitian matrices could move around inside inner products without being adjointed. In this case, the unitary matrix is multiplying both vectors X and Y, but because U is unitary, the theorem says that we can just take them off. So they don't move around, they just go away, or simplify. So Ux inner product with Uy simplifies to just the inner product of X with Y. If we think of the norm of a vector as measuring its length, this part tells us that the length of U times X is the same as the length of X. So multiplying a vector X by a unitary matrix does not change its length. The proof of the first part uses our standard trick that we have used before where we write an inner product as matrix multiplication. So we write the inner product of Ux with Uy as the adjoint of Ux times Uy, and then we use properties of adjoints. The adjoint of Ux is the adjoint of X times the adjoint of U. And here we use the fact that U is unitary. U star X is just equal to the identity. The identity times Y is just equal to Y, and X star Y is the inner product of X with Y. The second part is proved using the definition of the norm. The norm of Ux is the square root of the inner product of Ux with itself, but because U is unitary, the inner product of Ux with itself is just the inner product of X with itself, and the square root of the inner product with X with itself is just the norm of X. and that proves the theorem. So we saw how to use non-singular matrices to solve multiple systems at once. We saw how to figure out if a matrix is invertible, and if it is, how to find the inverse. And then we saw how unitary matrices behave inside inner products.